Welcome back to the deep dive. This is where we take all the complexity of modern technology.
Yeah.
I'm talking about the endless documentation, the internal research notes, those super dense architectural diagrams, and we try to turn them into clear, structured, and hopefully immediately useful insight for you.
Yeah, and our mission today is really to cut through a lot of the jargon. We're not just here to define a list of tools. We want to define principles. The goal is to give you this operational framework so you can really understand the why behind technology choices and hopefully can gain that knowledge quickly, but also thoroughly.
Exactly. And today we're diving into a domain that I think for a lot of people feels a bit like a black art until you really get the basic mechanics down. We're talking about operations and monitoring, or O&M.
hmm
This is truly the heartbeat of every application that's running out there, and if you don't get a handle on it, your cloud deployment is basically just flying blind.
It really is. And we're going to be diving deep into the Google Cloud Operations Suite today, specifically because their set of tools provides just a perfect structured map for understanding these core concepts. We're really just trying to lay the essential foundation, custom tailored for anyone who needs to get fluent in O&M and fast.
Okay, let's unpack this.
Yeah.
To even begin to approach a topic this fundamental, especially if you're venturing into operations for the first time, we absolutely need a unifying analogy. Otherwise, logging, monitoring, tracing, profiling, they just all blend together.
Oh, they do. It becomes this one big, overwhelming pile of data, and you don't know where to start.
Right.
So absolutely. Let's start with an analogy. I want you to think of operations and monitoring as managing a massive high-performance factory, maybe one that builds, I don't know, complex medical devices or autonomous cars 24/7. It never stops.
Okay, so high stakes, thousands of moving parts, and lives could literally depend on it running smoothly. A nonstop factory.
pretty
Like
awesome.
it. Perfect.
Exactly. Now, in that factory, there are two major, and I mean entirely distinct, pillars of O&M. They answer totally different questions, they use different systems, and just recognizing this separation is probably the single most important concept we can cover today.
Okay, so what are those two pillars? And what are the questions they're trying to answer?
So first, you have logging. This is the black box, the comprehensive ledger. It is the system that records every single action, every event, every failure, every command, exactly as it happens.
Okay.
So logging tells you definitively what happened. It's a forensic historical record. You need it for debugging, for compliance, for any kind of detailed post-mortem analysis.
So if a machine in our factory overheats, the log entry isn't just going to say problem. It's going to be something like machine 4A, temperature sensor reading 98 degrees Celsius, started cooling cycle, failed to initialize pump 2 at 20.15.33 UTC.
Precisely, in the raw narrative of everything that's going on. Then the second pillar is monitoring. This is the dashboard, the gauge. This system doesn't record that specific narrative event. It records the ongoing health and performance right now, continuously sampling the state of the system. So monitoring tells you how is the health at this very moment. And it's often displayed as, time series charts, percentages, graphs.
I see. So monitoring might track the average temperature of all machines over the last hour, or maybe the factory output rate per minute. It's an aggregation of the current status.
That is the critical distinction. It's the difference between the granular event streams, that's logging, and the aggregated continuous metrics, that's monitoring. And what's fascinating here is that this separation lets us use different tools for completely different tasks.
How so?
Well, we need that monitoring dashboard to be lightning fast for real-time viewing, right? That means you can't have it bogging down, searching through petabytes of individual log entries. And conversely, we need that logging ledger, that black box, to be immutable and comprehensive so we can investigate it later. You can't compromise one for the other.
That clarity helps a ton. Seriously, if you're just starting out in operations, just getting that difference between the historical record, logging, and the real-time status check, monitoring, that's the foundation for everything else.
It is.
So let's jump straight into that first pillar then, logging the comprehensive chronicle.
Let's do it.
We're kicking things off with cloud logging, which is Google's system for collecting, storing, and analyzing all those event streams we talked about, the ones generated by your apps, your operating systems, and the underlying cloud infrastructure itself. It's really the central nervous system for data collection.
And that brings us right away to the first real operational challenge: reliable data ingestion. I mean, if you're running these highly scalable containerized environments, like say something powered by Kubernetes engine GKE, How does your application safely and reliably get those facts, those logs, to the centralized system?
The source material is actually really clear on this,
Yeah.
and it points to a best practice for modern cloud-native design. The Google recommended sort of native way for GKE workloads to output their logs is to simply write to standard output, stdout, and standard error, stdout.
Okay, this is a really fundamental concept in modern architecture, and the why behind it is absolutely everything. Historically, we would write logs to a file, right? Maybe varlog, myapp.log, something like that, inside the server.
Sure, that's what I've always done.
But containers are inherently ephemeral. They're designed to spin up, handle a burst of load, and then die quickly, maybe hundreds of times an hour. If you write your logs to a file inside that temporary container, what happens when it gets recycled?
Oh, the log data is gone. It just vanishes with the container.
It's gone forever.
Right.
So by directing logs to stdout or start, the application itself isn't worrying about persistence at all. It's just shouting its information out into the void. This means the developer's code is completely decoupled from the logging infrastructure.
Shouting into the void. I like that. So the magic has to happen somewhere else.
Exactly. The magic happens beneath the container. The underlying GKE node, the virtual machine it's running on, has an agent. It's usually a version of Fluent or Fluentbit. And that agent is specifically configured to intercept all the data streams written to stdout and stderr by all the containers running on that node.
So it's listening to all the shouting.
It's always listening. It captures the data, it adds crucial metadata like the container name, the pod name, the timestamp, and then it automatically pipes that entire stream directly into the centralized cloud logging system. This makes sure the logs are durable, they're centralized, and they're rich with context, all without the application developer ever having to manage a single file system.
That eliminates a huge operational headache, and it definitely maximizes reliability. Okay, so now the data is captured. We have to talk about how we move it around. In a big organization, data doesn't just sit still. Logs often need to be moved out of that primary environment, right? Maybe for long-term storage, for compliance, or, and this is a big one, for integration with existing corporate tools.
Yeah, this brings us to the really crucial process of routing and exporting logs. One of the most common requirements you'll see is streaming all your audit logs, all those sensitive records of who did what and when to a third-party security platform, something we call a SIEM.
Wait, let's stop there. We should probably define SIEM, because that's critical context for this.
Good call. A SIEM, that's SIEM, stands for Security Information and Event Management System. It's basically a central clearinghouse for all of your security data. It collects security events from every corner of your network,
Yeah,
your firewalls, your servers, your cloud infrastructure, your applications.
and it puts it all together.
It puts it all together and applies analysis, correlating seemingly disparate events to spot sophisticated threats or track unauthorized activity. The key is, it needs all your logs in real time to function properly. Things like Splunk are a common example.
Got it. Okay, so if we need to feed this massive real-time security pipeline, how do we do it efficiently and securely? The sources suggest the standard pattern is to create a log sync in cloud logging with a pub subtopic as the destination.
Right, and this architectural choice is it's really elegant because it solves several problems at once. Just think about the alternatives for a second.
Okay.
If you tried to have the SUM system constantly pull the cloud logging API every few minutes, you'd introduce latency, you'd create unnecessary network load, and you'd probably risk hitting your API rate limits. It's clunky.
And I'm guessing the other option is just giving the SUM platform direct owner-level access to the logging data.
Which is a massive security risk. You don't want to do that.
Yeah.
So by using a log sync coupled with PubSub, you create this perfect decoupling layer. The sync configuration basically tells cloud logging, hey, whenever you see a log that matches this filter, for example, all audit logs, I want you to push a copy of that entry instantly to this messaging queue.
And that messaging queue is PubSub, which is a reliable asynchronous messaging service that provides guaranteed delivery. So the SIEM system just becomes a subscriber to that PubSub topic.
Exactly. It pulls messages at its own pace. This ensures the logs are delivered instantly, reliably, and without taxing the source cloud logging system. Plus, the SUM pool doesn't need to have those broad, risky permissions. It's a textbook example of using an event-driven model for both reliability and security decoupling.
That efficiency becomes absolutely mission critical when we pivot from just historical analysis to speed. I'm talking about fast reactions to immediate security events, closing that window between detection and mitigation.
Right. If you detect a serious anomaly like An unauthorized person attempting a login from a new country, or a sudden unexpected change to a critical firewall rule. You need immediate event-driven action. You can't afford to wait, not even a minute for a polling script to run, or for some batch job to process the data.
So, if the objective is the fastest possible response, the recommended Google practice here is to export logs to a pub/sub topic and trigger a cloud function with the relevant log events.
This is where O&M really transitions from just observation to active defense. A cloud function is a serverless compute platform. It's essentially just a tiny piece of code that only executes when it's triggered by an event. The moment that specific security log entry hits the pub/sub topic, that functions as the trigger. It instantly wakes up the cloud function.
And that function, armed with the exact log data from the event, can execute a predefined mitigation script in, what, milliseconds?
Milliseconds. We're talking about instantly reverting the unauthorized firewall change, or terminating a suspicious session, or locking down a compromised user account. It's turning a passive record-to-log entry into an active, automated, and preventative action with sub-second response time. You're moving from the model of, I heard the alarm, to the safety system automatically engaged the fire suppression mechanism. This level of automation is absolutely essential for operational security at cloud scale.
Okay, now let's scale up and consider the organizational challenges of logging. Trusting the data is one thing, but managing that data across a massive enterprise structure is a whole other beast. Large organizations don't have one cloud project, they have hundreds. They're typically organized into folders for different environments: dev, staging, prod.
And the operational requirement is almost always centralized log management. The question becomes, how do you ensure you capture logs from all the production projects, and this includes the ones that don't even exist yet but will be created next month, without having to manually configure every single one?
Because if you forget one, you have a compliance gap. You have a blind spot.
You have a huge blind spot. So you solve this by leveraging the cloud resource hierarchy. The solution is to create an aggregated export on the production folder, and you set the destination sink, maybe a cloud storage bucket, in a dedicated operations project, which is separate from the production environment itself.
That's a really crucial concept in cloud governance, isn't it? By applying that export rule at the production folder level, every single project that lives inside that folder, now and in the future, just automatically inherits that rule.
That's it. It ensures centralized collection is enforced organization-wide, no matter which individual engineering team spins up a new project. It's hierarchical enforcement, and it's how you solve the complexity of scale.
That's centralized control that enables distributed development teams. It's a perfect operational balance. Now, let's shift focus back to security for a moment. Trust. How do you ensure that the log data itself, that forensic ledger we talked about, has not been tampered with? A malicious actor could easily try to cover their tracks by modifying or deleting log entries.
This brings up the requirement for non-repudiation and verifiable data integrity. It's a key business objective, especially in highly regulated industries like finance or healthcare. Just relying on access control to the logging system isn't enough because insiders can still pose a risk.
So we need more than just permissions. We need cryptographic proof that the data hasn't changed since the moment it was recorded. The high-integrity solution, then, is to design the logging system to digitally sign each timestamp and log entry and store the signature.
Yeah, this moves log management into the realm of chain of custody. Think of a digital signature as a tamper-proof seal on an evidence bag. It uses cryptographic hashing to generate a unique fingerprint of the exact log data and the exact time it was recorded. If, 5 years down the line, someone alters even a single character in that log entry, the stored digital signature verification will fail instantly.
And that's not just a technical flourish, is it? It's an absolute requirement for forensic analysis. You need verifiable proof, not just a promise, that the log entry is exactly what the system recorded at that moment. This supports everything from internal debugging all the way up to external regulatory audits.
Precisely. And that pretty much wraps up our deep dive into logging the comprehensive record. Now let's transition to Section 2. Monitoring the real-time health dashboard, which, as we said, operates on entirely different principles.
Okay, so if logging is the ledger of past events, monitoring is the crystal ball showing us the present. And we have to clearly define the fundamental building blocks here: metrics versus alerts. I feel like these are often confused, but they serve fundamentally different purposes.
They absolutely are. Let's go back to our high-performance factory. Metrics are the raw, continuous measurements pouring in every second. They're the speedometer of the conveyor belt, the thermometer measuring the coolant temperature, the voltage regulator reading. Metrics track resources, performance, and the operational state of the system.
So a metric is just passive data collection. It's a number reported over time. For example, CPU utilization is 45% or network latency is 15 milliseconds. Just tells you what the system is doing.
Correct. An alert, on the other hand, is the action system. It's the result of applying critical operational logic to the metric data. An alert is the automated trigger that fires when a metric crosses a predefined dangerous threshold. It's that red light flashing on the dashboard coupled with the system that pages the on-call engineer at 3 a.m. It tells you when the system has entered an undesirable state.
Okay, that makes sense. So if we have a requirement to be alerted via email whenever the CPU utilization of a compute engine instance group exceeds, say, 80% for more than 5 minutes, we are not setting up a log query. We are configuring an alerting policy.
And that configuration is handled specifically by a cloud monitoring alerting policy. This is the tool that's specialized to watch those continuous metric streams and trigger notifications based on defined time and value thresholds. And you highlighted the crucial criteria there for more than 5 minutes.
Yeah, why is that time window so important? Why not just alert immediately when the CPU hits 81%?
This is a key operational best practice, and it's designed to combat what we call alert fatigue. Systems are inherently noisy, they're bursty. Imagine a background process runs for 45 seconds and it temporarily spikes the CPU to 95%. That's normal system behavior. It's not an operational failure that requires a human to wake up and intervene.
Right. If you alerted on every single momentary spike, your engineers would just start ignoring the constant noise. And that's when they'd miss the real crisis.
That is exactly when they miss the real crisis. So that 5-minute grace period confirms a sustained operational issue. It confirms that the system is genuinely under stress and it's not just handling some transient workload spike. Monitoring policies have to be engineered to filter out the noise and only flag the sustained failure states.
So the effectiveness of your monitoring isn't measured by how many alerts you generate, but by how accurately and how sparingly you alert on problems that genuinely need human attention.
100%.
Okay, let's move into a much more complex and nuanced area of monitoring, autoscaling. This is where we really need to dive into the technical details of what these metrics truly represent.
Yeah, this is a great one. Consider the scenario. You have an application that needs to autoscale. So, to provision new server instances, whenever the total system memory usage exceeds 80%. You deploy the monitoring agent, you set the target metric to memory percentist, but under heavy load, the system starts thrashing and slowing down before it ever scales. The scaling threshold isn't working like you thought it would.
This sounds like a false negative in your monitoring. Why would a simple used memory metric lie to us like that?
Because operating systems, particularly Linux, are incredibly smart about memory management. When an OS reports its memory usage, it typically breaks it down into several different categories. The metric memory percentist often only reports the memory that's actively claimed by running applications. However, memory is also used for things like file system caches, cached, temporary system buffers, buffered, and kernel structure overhead, slab.
And the OS can quickly reclaim that buffered and cached memory if a new application suddenly needs it. So that memory is technically used from the OS perspective, but it's functionally available to new processes.
Precisely. So if your autoscaling rule only monitors the memory that applications have actively claimed, the used part, it's ignoring the memory currently occupied by the system cache. If that system memory cache is already huge, meaning the kernel has reserved a lot of RAM for efficiency's sake, the total system memory pressure is actually much higher than what that simple used metric is telling you.
And for those who might not be familiar with slab memory, that's where the kernel manages its own internal data structures, right? Things like inode caches or entry caches. Basically, the OS's own internal accounting tools.
That's right. Let's go back to the factory floor. The used memory is the raw material that's actively being worked on by the robots right now. Cache memory is the raw material sitting neatly staged on the floor, ready to go. Technically, it's reserved, but it's reclaimable. And slab memory is the space that's reserved for the engineer's essential workbenches and clipboards.
So if we only look at the raw material on the robot's bench, we miss the fact that the entire factory floor is jammed up with staging areas and administrative tools.
You've got it. Relying only on that simple used metric gives you a false sense of availability. If we want our autoscaling policy to accurately reflect the total system memory pressure, that moment when the whole system is nearing congestion, we have to account for all of these relevant memory states.
So what's the fix? How do you get that more accurate picture?
The solution detail that the source material points to is specific and it's highly technical, but it's crucial for successful operations. The autoscaling policy needs to change its filter to include metric.label.state equals used, ANED metric.label.state equals used AND, metric.label.state equals cached, ANED metric.label.state equals slab.
Wow, okay.
By combining all of those specific states, you get a much more accurate composite metric of memory pressure, and that ensures the application scales up before the slowdown becomes critical for your users.
That is an amazing level of detail. It just shows that effective monitoring goes so far beyond just reading the label on the dashboard. It requires real operational intelligence about how the underlying operating system actually works.
And this brings up an important related issue. Integrating new cloud monitoring with your existing mature organizational practices. A lot of large organizations have deeply invested in Prometheus monitoring, for example. They have vast libraries of custom dashboards, complex PromQL queries. They love their query language.
And those teams are often, let's say, reluctant to abandon that cognitive investment just to move to a new cloud platform. They want the benefits of the cloud, but without the operational friction of retraining every single engineer on a brand new querying system.
Google saw this resistance and addressed it directly. The dedicated solution is the Google Cloud Managed Service for Prometheus. It's a perfect bridge technology designed for that exact scenario.
So you get to keep using your existing Prometheus query language, your PromQL, and you maintain your familiar workflows, but you get to offload the entire operational headache of the Prometheus backend infrastructure. Things like storage, scaling, retention, high availability.
It's the best of both worlds. The engineers stay productive in the language they already know and love, but the organization benefits from the scalability and reliability of Google's managed infrastructure. It really minimizes that operational barrier to cloud migration.
Okay, finally for this section, let's talk about metrics retention. Metrics can accrue data at an incredible rate. If an organization has a really stringent compliance requirement, say retaining metrics from all of their applications for 5 years for future legal analysis, that volume of data is just staggering. It far exceeds the default retention policy.
Oh, yeah. Default retention is typically measured in weeks or months, not half a decade. For something like that, you need massive, reliable, and critically cost-effective archival storage.
And our sources confirm the necessary approach here is to configure Stackdriver monitoring for all projects and export the metrics to Google Cloud Storage, GCS.
And the choice of GCS over, say, BigQuery is a strategic operational decision. It's based on cost and access patterns. BigQuery is optimized for high-speed analytical queries,
Right.
and you pay a premium for that speed.
Right.
GCS, on the other hand, is built for massive object archival. It's significantly cheaper per gigabyte for data that you're not going to access very often, which is exactly the profile of historical compliance data that you might only need once a year for legal discovery.
So we're making a deliberate trade-off. We're sacrificing that instant query speed for 5-year plus petabyte scale archival cost efficiency. The operations team has to choose the right storage tool for the job requirement. It's not one size fits all.
Never is.
All right, we've established the foundation of logging and monitoring. Now let's move into Section 3, where we get to discuss the highly specialized diagnostic tools. This is the difference between a check engine light and a full engine teardown.
First up is Cloud Trace. Trace is absolutely essential in the world of microservices. When a single user request hits your application, it doesn't just hit one server anymore, right? It might traverse 5, 10, even 20 different services, databases, and queues before it finally returns a response to the user.
And the scenario we're diagnosing here is when your standard monitoring says, hey, average latency is 150 milliseconds, everything's fine, but you're still getting a small number of users reporting that some requests are taking 30 seconds or more. These outliers are ruining the user experience, but you can't see where in that long chain the slowdown is actually happening.
Exactly. Standard monitoring is completely blind to that internal request path. To solve this, you need to instrument the application with Stackdriver Trace in order to break down the request latencies at each microservice.
I love the analogy of Trace being like a GPS tracker. It's like you're putting a unique identifier, a correlation ID on the transaction the moment it enters the front door, and then every single service it touches reports back, I started processing at this time, I handed it off at this time.
That's a perfect description. Trace then stitches all those individual reports, which are called spans, into a single timeline visualization. So when that slow request finally returns, Trace shows you visually whether the bottleneck was the authentication service or the billing microservice or a specific database query within one of those services. It pinpoints the latency bottleneck that's hidden deep inside that distributed network.
Without Trace, you're just guessing. With it, you get a forensic end-to-end timeline of the entire request.
Now let's shift from request latency to resource consumption with Cloud Profiler. This addresses the other great operational headache, the CPU hog.
We're looking at an application, maybe it's running Java on Compute Engine, that's consuming an excessive amount of CPU, and that's driving up costs. But the critical construct here is that the issue cannot be reproduced in staging. It only happens in production, and we need to analyze the live production code with minimal performance overhead.
This is the classic observer effect problem. If you try to attach a traditional deterministic debugger to a live production process, you slow the whole process down, you change the timing of everything, and often that elusive performance bug just vanishes. You can't see it anymore.
Because you change the conditions by observing it. So we need deep code analysis without heavy instrumentation. And that's why Cloud Profiler is the tool of choice.
Profiler works on the principle of continuous statistical sampling. It doesn't stop the world to trace every single function call. Instead, it periodically and randomly samples the call stack of the running application, maybe every few milliseconds.
So it's a bit like taking quick random snapshots of our factory floor every minute. No single snapshot is a full record of everything, but over the course of a day, you build up a very clear statistical profile of where the machines are spending most of their time.
Precisely. By aggregating thousands of these statistical samples, Profiler can accurately identify exactly which functions, down to the line of code, are consuming the most CPU time or memory or wall time all, while imposing a negligible performance penalty on the production system. It's absolutely essential for resolving those performance issues that are unique to the highly complex real-world traffic patterns of a live production environment.
It transitions you from knowing that your CPU is high, which is what monitoring tells you, to knowing why your CPU is high, which is what Profiler tells you. And that's the level of insight you need to actually fix the underlying code issue.
Couldn't have said it better myself.
That moves us nicely into Section 4, Operations Best Practices and Reliability. These are the decisions that really ensure your architecture plays nicely with the cloud environment it lives in.
Let's start with a classic deployment challenge. You have a tiny Python web application. It requires minimal resources, let's say only 0.1 CPU cores and 128 millibit of memory. It needs reliable deployment and, most importantly, high machine utilization to be cost-effective.
Right. If we were still operating in the traditional VM world, we'd probably provision a full, small VM, maybe an N1 standard one for this one tiny service. And that machine would be sitting at, what, less than 10% utilization? You'd be running maybe 10 small apps on it, that total 10% of the machine's capacity. That's a huge waste of money.
It's an incredible waste. And traditional VM management, where you might have to restart the instance for every deployment, introduces huge reliability risks and very slow deployment times. This is the exact problem that drove the entire industry toward container orchestration.
So the recommended solution is, of course, containerization using Google Kubernetes Engine or GKE.
And the operational benefit here is all about efficiency. GKE allows you to take dozens of these tiny workloads, containerize them, define their exact resource requirements, 0.1 CPU, 128 millibit, and then Kubernetes handles all the scheduling. It packs them densely onto larger shared machines, ensuring the underlying compute infrastructure is utilized close to 80–90%. This is utilization maximization at its finest.
And the deployment process itself becomes incredibly reliable. You build the Docker image, and then you just create a Kubernetes deployment object.
That deployment object, it manages the rolling updates automatically. It ensures that traffic shifts gradually from the old version to the new version. It guarantees a minimum number of replicas are always running, and it handles self-healing if a deployment fails. For instance, a small detail like setting the image pull policy to if not present in staging environments can optimize speed by not needlessly re-downloading the image if it's already cached on the node. GKC is the operational choice for scalable, reliable, and cost-efficient management of many small services.
It really demonstrates why the architecture matters so much.
Yeah.
Container orchestration is fundamentally an O&M solution to the utilization and reliability problem of microservices.
Now let's talk about resilience, disaster recovery, or DR planning. You have to develop procedures to test your mission-critical application's DR plan. Google recommended practices require 2 native capabilities to make sure the process is repeatable and verifiable.
Yeah, you can't be manually rebuilding an entire regional deployment during a disaster drill. It would take way too long, and you'd absolutely introduce human error.
You would. So first, you need provisioning automation. You use Deployment Manager or a similar infrastructure as code tool like Terraform to automate the service provisioning and the infrastructure setup in the recovery region. This ensures the rebuild is fast, it's reliable, and it's auditable.
Okay, that's step one. But second, you need visibility into the outcome of the test. You need to verify that the application didn't just come back online, but that it came back correctly with all of its dependencies intact and working.
And for that, you use Stackdriver, which is the broader encompassing term for logging and monitoring, to observe, to track, and to debug the results of the DR test. You're monitoring resource metrics, checking logs for any critical initialization errors, and you're tracing test transactions to make sure performance targets are being met in the new region.
So it's automation for the build and observation for the validation. That sounds like solid DR planning.
It is.
Now, I want to challenge this next point, because this is something that often causes massive friction between development and operations teams. We have a lead engineer who is proposing a new application design, and it uses WebSockets and HTTP sessions that are not distributed across servers.
Oof. Okay, so what that means is once a user establishes a connection with server A, every single subsequent connection from that user must hit server A, otherwise their session breaks and they lose all their work.
Which sounds like an operational nightmare.
It is. It's a nightmare because modern cloud load balancing is designed to maximize resilience by distributing traffic evenly and randomly across all the available servers. If you deploy this non-distributed application behind a standard cloud load balancer, that app will fail. And it will fail spectacularly under any kind of real load.
This highlights why O&M has to be involved in the design phase, not just after deployment. The operations team needs to intervene early. The recommended action here is to meet with the cloud operations team and the engineer to discuss load balancer options, specifically sticky sessions or session affinity.
Right. The operations team is the arbiter of the external platform constraints. They're the ones who manage the load balancing service. They understand its capabilities and its limitations.
Exactly. The developer decided the application must use non-distributed sessions, maybe because of some legacy code or a specific framework limitation. It's the ops team's job to provide the mitigation. And that mitigation is configuring the load balancer to activate session affinity or sticky sessions.
This forces the load balancer to remember which server a user connected to first, and then it routes all subsequent traffic from that user back to that same exact server. It ensures the application runs properly, but, and this is a big but, it's a critical operational decision that introduces complexity and it reduces resilience. If that one sticky server goes down, that user is completely cut off.
But it prevents the engineering team from unknowingly building an application that is fundamentally incompatible with the cloud's architecture for high availability.
That's the key. Finally, let's wrap this section up with continuous improvement in logging tools. An application team is dissatisfied with their current logging solution. They need something better for capturing errors and for detailed historical analysis for their new cloud product. They come to the operations support team and ask, what logging tool should we use?
The intuitive response for an ops person might be to just immediately suggest a Google Cloud product, like, hey, just install the Stackdriver agent. But our best practices source material actually recommends a more consultative approach.
Yeah, the best practice is not to dictate a tool, but to help them define the requirements and assess viable logging tools. This is the real essence of consultative O&M.
Why is that so crucial, though? Why not just give them the standard answer?
Because the operations team needs to understand the nuance of the application's specific need. Do they generate 10 gigabytes of logs per day or 10 terabytes? Do they need real-time streaming, or is batch analysis going to be sufficient? Is the primary goal security compliance, which would require digital signatures, or is it performance debugging, which requires super quick searchability?
I see.
Recommending a heavy, expensive SIEM solution when all they really need is basic error reporting or vice versa is an operational mistake. Defining the requirements first ensures that whatever solution they select truly meets their specific volume, retention, security, and analysis needs.
It's leading with process and requirement definition, not just product prescription. A subtle but really important difference.
It is.
Okay, wow. That was a lot.
To summarize this pretty extensive deep dive into cloud operations and monitoring, we really started with that critical distinction that defines the entire field. Logging is the detailed forensic ledger of what happened. Monitoring is the real-time health dashboard, answering the question, how is the health right now?
We saw how efficient cloud-native architecture really demands that containerized applications write their logs natively to stdout and stderr, We then witness that powerful shift from just passive record-keeping to active defense, using pub/sub syncs to provide instant, event-driven triggers for automated security responses via cloud functions.
We also stress the operational necessity of separating metrics. That's the raw data, like CPU usage, from alerts, which is the action system that only pages someone when sustained failure thresholds, like that 5-minute grace period, are crossed. And crucially, we detailed how effective autoscaling requires deep technical knowledge, forcing us to monitor composite metrics that include cached, buffered, and slab memory, not just those simple used metrics.
And finally, we covered those specialized tools that are essential for deep diagnostics. Trace, which puts a GPS on complex transactions to pinpoint latency bottlenecks in microservices, and Profiler, which uses statistical sampling to hunt down those elusive, production-only CPU hogs while minimizing the observer effect.
The foundational takeaway here is that O&M requires intentional, strategic choices, using GKE to solve utilization problems, using infrastructure as code for verifiable DR testing, and ensuring that application design choices like session affinity are operationalized correctly through the load balancer.
What does this all mean for you? Well, you now have the framework to look at any running cloud application and identify its operational posture. You can move beyond just passively observing your systems to actively defining them. If you're building or maintaining a system, the first operational question you have to ask is not what tool you should use, but what specifically defines health and failure for your specific business logic and your user expectations.
And we spent a considerable amount of time discussing how combining log exports with automated functions, that's pub/sub and cloud functions, turns observation into immediate reaction. This is the paradigm shift in modern operations.
Given that powerful combination, what is one manual operational task that you or your team perform today? Maybe it's validating a specific set of service account permissions after a deployment, or checking log files for a key initialization string on startup that could be turned into an instant automated reaction using these cloud operations tools. Think about how you can automate not just the application, but the operational response itself, using logs as the trigger. That's the true power of this whole suite.
Something to mull over until next time.
That's it for this deep dive. Thank you for joining us.
We'll see you on the next one.